There is much easier math in this topic than in Chapter 9. So if you were out for the AP US History test on Friday, you really need to make sure that you review that stuff that we did in class. Okay, there's a video posted under videos in class. It'll say Chapter 9 math examples or fluid mechanics math review or something like that. And the worksheet for that is listed under documents and handouts.
What are the sections that Chapter 9?
Not Chapter 9 and 10. Chapter 9 and 10. So, Section 10.1 is about temperature and thermal equilibrium. We're going to talk about temperature and kinetic energy, thermal equilibrium itself, and then temperature scales. Okay, so those are the three main objectives here. A lot of this beginning you should recall from some chemistry and some physical science stuff.
Are we section 1 or 2?
We're starting 10.1.
Like class-wise, because it said on Google that this was due today.
Yeah, but if for section 1 minutes.
Probably if you go to class then, probably not for you guys.
But aren't we section 2? Like we have done it.
You're section 2.
It says section 1 is due tomorrow.
It's because, you know why it says that? Because I originally was doing this on Friday, but because so many of you were out for the AP US, I did a math review instead. So there was no, besides the lab due last night, there was no homework due today.
Okay. 10-1 will be due tomorrow. And then
Well, for you guys who don't have me tomorrow, but yeah, Wednesday. Alright. Anyway, so temperature. Temperature is simply the measurement of the average kinetic energy of the particle. So, if the temperature of an object increases, what that means is that the particles are vibrating at a higher frequency or at a higher rate. They're moving faster. And what you usually see an example of this is with gases. The easiest way to visualize this. The particles in the gas move faster as the temperature itself begins to increase. Okay, now if the volume can be expanded of the object, that affects it as well. The concept is that it's a measurement of average kinetic energy. Looking at an example of this, all we're seeing is that as you add energy to the system, the temperature increases. Okay, adding energy to the system, the temperature itself increases, and vice versa.
So you're not adding more particles, it's just speeding up, right?
Correct. So increase in temperature just means that they're moving faster. Not more particles, but moving faster. So let's talk about temperature being a relative term. Okay, a relative term. So look at the two examples here. We've got a glass of ice water, and then we've got a cup of hot chocolate. Okay, glass of ice water and a cup of hot chocolate. Now, when you touch these two objects, what would you say? What would your statement be?
Well, depending on how cold it is, maybe you could it was too hot, it's like, ooh, that's not.
Yeah, so you'd say that the ice water is really cold and that the hot chocolate is really hot. Now, it's a relative term though. What do I mean by a relative term?
The hot coffee is only hot because you're comparing it to the outside temperature. So if the outside temperature were hotter, it could be not as hot temperature.
So imagine you have like 102 degree weather, right? And you had a coffee, and the cup of coffee was like lukewarm. It probably wouldn't even taste hot at all. It would taste room temperature based on the temperature outside. Also based on your body temperature. When you touch a glass of ice water, it feels cold because your body temperature is greater than the temperature of the glass of ice water. What's body temperature? 90, what is it? Alright, 98 Fahrenheit, right? Around 100 Fahrenheit. Ice water is like, we're talking in the 30s. High 30s, low 40s at the temperature of ice water when your body is 97. So you touch the cup of cold water and it feels cold relative to your hand. And if you touch a glass of hot cocoa or hot chocolate, that's at a temperature of like 180 degrees Fahrenheit, because it was using boiling water, which boils at 212. You know it's going to be hot, it's going to be in the hundreds. It feels hot because it's higher in body temperature. So it's a relative term, temperature. Maybe imagine that there's another race existing in the world or in the galaxy, this Martian race, this alien race, and this alien race has a body temperature of 180 degrees Fahrenheit. Well, then hot chocolate wouldn't feel that hot to them. But a glass of ice water would still feel very cold, relatively speaking. Okay, relatively speaking. for another bonus for you guys. Okay, for another bonus, an opportunity for you. And this is interesting. You definitely want to try it. You want to try it out with 2 separate containers. Okay, take 2 containers, make 1 container really warm water, 1 container really cold water. Don't make it hot enough that you burn your hand, right? But make it warm enough that you can feel it. It's kind of hot. Make the other one pretty cold, like an ice bath. Put 1 hand in each of them. So put 1 hand in the ice bath, put 1 hand in the really, really warm water. Not burning warm, but warm enough. Hold them there for like 30 seconds. Then take them both out and put them in a bowl of regular temperature water, like room temperature. Okay? Try it and see what happens. Describe what's happening. That's your bonus. Okay, so again, 1 hand is in ice water, 1 hand is in hot water. Take them both out, put them in room temperature water, and tell me what you feel. Okay? Don't tell me now. So tell me in the video. Explain what you're feeling. Question.
Can we work on that together? Like
Uh,
alternate videos? Like-
sure. I want to see both of you doing it though. So if you work with the partners in this recording, I want you both to describe what's happening. And I want to see you both trying it. Because it's more of a sensation that you'll feel. So I want you to actually try it yourself. Okay? Alright. By the way, if you guys do these bonuses, I recommend you email me, just let me know sometimes, because I don't always look in your Dropbox folder like every 2 seconds. So usually if you do a bonus, it's good to say, hey Mr. Howell, here's a link to the video, or I put it in Dropbox. Okay, same for the lab. Like a lot of you for the lab either use a link, which is fine, and if you uploaded like a Lab 15 document, and just put the link in the document, that's fine also. But some notification of sorts, right? Don't just put a link on YouTube and never get me the links in there.
This is kind of a video, I don't want to waste time, but I told him on Friday that I was going to show you the videos. Nah.
The extra, yeah, show me if you're free, maybe next period or the period after.
Okay.
Okay? So for thermal equilibrium, what we're going to talk about, like force equilibrium. Okay, force equilibrium is when 2 forces combating each other are balanced. Right? An object is floating when the gravitational force is balanced by the buoyant force. That's force equilibrium. For thermal equilibrium, these 2 objects in contact have to have identical temperatures. If they don't, what's going to happen? If 2 objects in some sort of contact don't have the same temperature, what happens as a result?
Would they go to like a happy medium?
Yeah, they have to eventually find a medium or a middle temperature. So what will happen is take your hand, for example, place it on the desk. The desk is not ice cold, but it's definitely colder than your hand is. So believe it or not, over time what will happen is your hand itself will want to come to an equilibrium temperature with the table. Well, your hand is not going to decrease in temperature much. So what's going to happen to the table temperature? Yeah, it's going to get warmer where your hand is. Hold your hand there for long enough, and then touch it, you'll feel the table's warm where your hand was. Simply because your table, or the table, wants to reach equilibrium with your hand.
With a warm chair.
Say again?
With a warm chair.
Like in a warm chair. When you sit in a warm chair, it doesn't mean somebody farted. It means that you're just sitting in the chair for a while. Okay, usually.
What's in a chair?
Usually.
Hey, was there that thing where you were, Mr. Howell, something? How does it work when you keep your hands in warm water and you pee?
I don't know. I'm not sure why it makes you pee. I'm not actually sure.
Like when you're sleeping?
I don't know. I think it's more biological than physical. I'm not really sure what's happening there.
When you do that, like maybe extra.
No. Alright, let's talk about thermal expansion. Thermal expansion was something that you talked about in chemistry class. Okay? And in chemistry, when you talk about thermal expansion, you're talking about the fact that as the temperature of something increases, generally, the volume increases. Okay? In general. There are exceptions, and we know that H2O is one of the biggest exceptions. The minute it freezes, it actually expands. So for water, when water freezes, it does the opposite. Instead of the volume getting smaller, the volume gets larger. And that's again because of a hydrogen bomb. It's an exception to this general rule. The general rule can be seen here with a mercury thermometer. The mercury thermometer works in a way such that it's a very, very thin tube. And that tube has mercury at the bottom of it. And when the mercury temperature increases, what happens is the volume wants to expand. But because the tube is fixed, it starts to rise up in height. The diameter of the tube is the same. If the volume increases, it's got to go somewhere, so it starts to increase. It looks like there's more mercury. It's not. It's just the volume is getting larger and larger, so it starts to fill up the thermometer. As the temperature gets higher, you see the level of mercury go up, and as a result, you measure the actual temperature. So this is an example of thermal equilibrium. In chemistry, if you ever took a thermometer and placed it in a beaker that was heating, say there was a fluid that was heating, you're trying to make a supersaturated solution. So you heat up this fluid, you keep adding the solute, supersaturated, so you can keep adding like salt as the temperature gets higher. Well, if you put a thermometer in, it's going to start to increase the temperature. But you need to give it a little bit of time, right, to level off. You can't put the thermometer in and read it right away, because the thermometer is going to read room temperature. The minute you put it in the beaker of boiling fluid, it starts to increase, but you need to give it time to reach thermal equilibrium. Once it reaches thermal equilibrium, the level of mercury, or is it iodine in the new ones now, I think? What's in the new thermometer? It's not mercury. It might be iodine. I don't think it's iodine though, it's something else. Alright, but whatever it is inside of there, it increases in volume until the actual temperature of it is the same as the temperature of the fluid that the thermometer is submerged in, and it levels itself off and it stops increasing. At that point, you reach thermal equilibrium, thermal expansion is completed, and you can measure the temperature of the fluid. What are some examples of this in everyday life? Thermal expansion is really, really important. It happens all the time whether you realize it or not. You have to take it into consideration. Think about like the seasons. What happens in the seasons? Change in temperature and pressure for sure. What are some examples of this change in temperature that causes either A, a change in pressure, or a change in volume?
Could be like hail.
Hail?
Like if it hails, like it's normally a rainfall, but because the temperature is so cold that it's warm.
Okay, but that's not expansion, that's like thermal equilibrium. But where does the volume change? The volume of hail is just layer on layer on layer on layer of ice. But where does something actually change in volume in different seasons?
Well, it would be bodies of water getting more volume, ice, rain. Not rainfall, but like melting snow and like.
Yeah, significantly, probably not much, but that's an example, sure. What's one that's more significant?
I mean, it might be really wrong, but like, in my summer, I think there's a lot of stuff made out of wood, and in the summer, like, the heat makes it swell.
Yeah, that's exactly right. In the summer, your wooden doors will swell. And what you'll notice a lot of the times, you go to close the door, and suddenly the door doesn't really close fully. It gets stuck. It's sticky in the summer. You go to open the door, and you hear like a pop at the top of the door. Because the door is expanding in the summer. It's one good example. What else? Other examples?
Sidewalk.
Sidewalks. Yeah, what about them?
Isn't there like room, like they leave boxes that they leave them on so that you can expand?
Exactly. Ever walk on the sidewalk, notice they're in strips, they're in panels, and in between the panels usually there's like almost like the material is called caulk, C-A-L-K, for caulking. You can caulk things, which is like an insulation.
Wait, what's it called?
Now, you put it between the tiles of the sidewalk so that the sidewalk can expand without breaking. Now,
So the
have you ever driven on a highway, and what'll happen is this. In the winter time, the roads in the winter will start to contract. And what'll happen is there'll be cracks in the road. And then those will cause potholes in winter. When there's changing in temperature, the expansion and contraction of the asphalt, okay, the asphalt will cause potholes. In the summertime, or let's see, what about the winter time of your car? What do you notice about your car in the winter time or your bike?
Pressure.
Yeah, the tire pressure changes. The air actually contracts, changing the pressure, which can flatten your tire in the winter. That's why usually, well not usually, but nowadays, instead of putting oxygen in tires, what do people put? Anyone know? Yeah, nitrogen. Okay? A lot of cars are filled with the nitrogen and oxygen compound now of gas. The reason is so that in the winter, your tires don't flatten. Nitrogen itself has a lower thermal expansion coefficient, so it won't contract as easily as oxygen will. So a lot of the time now, if you go to new car dealerships or You get a new car, or even like a car repair place, they'll have a machine that is no longer just oxygen, it uses nitrogen. What they do, they deplete your tires by removing all the air, and then refill it with this nitrogen mixture. Okay, it's nitrogen gas mixture. All right, another good example would be bridges, but bridges are the same as sidewalks. Bridges are made in sections so they can allow for expansion and contraction, and they can also allow for some vibration, because the wind will cause the bridge to itself vibrate a little. So some common temperature scales that we know of are Fahrenheit and Celsius. Here's our conversions. You don't have to memorize these. You could if you want to. Okay, you could if you want to. The 32, do you see the 32?
Yeah.
It indicates the difference between the freezing points of water in the Celsius versus Fahrenheit scale. What is the freezing point of water? 32 Fahrenheit. Or 0 Celsius. Okay, or 0 Celsius. So go ahead and plug in 0 Celsius here for TC. In your mind, what's 0 times 9/5?
Your mind.
Plus 32 gives you 32. That's where the freezing temperature comes from. Plug in the freezing temperature in Fahrenheit, 32. What's 32 minus 32?
0.
So the freezing temperature in Celsius is 0. Okay, so you can convert back and forth if you know one or the other. Okay, if you know one or the other. Let's see. Let's go next slide, which is a lot more, not difficult. It's not more difficult, but different. Okay, not more difficult, but different. So here, we're looking at a temperature scale in what are called Rankine and Kelvin. Rankine and Kelvin. Rankine correlates to Fahrenheit. Kelvin correlates to Celsius. And you'll see that if you look at the equation here. Rankine is approximately the same as Fahrenheit plus 460. Kelvin is around the same as Celsius plus 273. Now, they're not exact. It's really like 273.15 or 146. I'm giving you an approximation, so I use the approximation symbol there. What is the whole idea behind absolute temperature? You may have learned of this in chemistry or in physical science before this.
Is it when, like, no molecules?
Yeah. So 0 Kelvin or 0 Rankine is the absolute lowest temperature that can exist. It means the ceasing of molecular motion completely. Now, there's a whole idea about limits and concepts of calculus that are involved here. Think about it. How do you cool off a can of soda? What do you do? Put it in either what?
The sun.
A cooler or a fridge, either one, right? Something that's colder than the temperature of the can of soda itself. That's how you can cool off a can of soda. So if I want to get the can of soda to be, let's say I want the can of soda to be 45 degrees. I mean to have to put in a refrigerator that's less than 45 degrees. Or else it would not work. It would not work if it doesn't go in something less than 45 degrees. So as a result, what I can think about is the simple concept that I can never really reach 0 degrees Kelvin or Rankine. Because if 0 is the lowest temperature possible, to get there, you need to put that object in something lower than 0. Use the concept of how you cool something off. The way to cool something off is by putting it in something that's colder than it. How could you get something down to 0? You have to put it in something that's colder than 0. But 0 is the lowest temperature. So it's the lowest temperature, but you can never really get there. Okay, it's called a limit in calculus, or an asymptote. In calculus is a term. You know the term limit. Okay, use the word limit so you understand that concept. But the whole idea is that it ceases molecular motion. So we talk about 0 Celsius, right? 0 Celsius, that's freezing for us. But 0 Celsius is how many Kelvin?
So 273.
273. So there's a whole ways to go before you get to absolute 0. You can go, again, if you set this equal to 0, temperature Celsius, you get 273. What if you set Kelvin equal to 0? What Celsius temperature does that correspond to? Negative 273. So the Celsius scale, although we kind of stop at 0, because on Earth, once things are freezing, we don't really go below 0 a lot. Especially in the wintertime, that's when you'll see the temperatures go a little bit below 0 Celsius. but not that often. Okay, you're never going to get down to negative 273 degrees Celsius. Okay, or actually in this case, Kelvin. Kelvin in this case, and Rankine, for some weird reason, I don't know why, to be honest, but Kelvin is not considered degrees Kelvin. I'm not going to take off points, but just so you know, it's degrees Celsius, degrees Fahrenheit, degrees Rankine. But Kelvin, you would say, like 35 kelvins. Okay, different terms, okay? Jerks?
How low does nitrogen bring things, or like what temperatures like would you
I don't know. I'm thinking it's low on the scale. When we looked at almost zero conductivity for electrical conductivity, we were looking at things that were like 4 Kelvin. I'm not certain. You can look it up, the temperature, but I don't know what the actual number is. Okay, let's look at a mathematical example of this now. Hold up. Let's look at this table first so we have an idea of where numbers are. So we know 32 and 212, since we're in the US, we use Fahrenheit. In any other countries, 0 and 100 makes a little bit more sense, to be honest. Why does 0 and 100 make more sense? Yeah, there's easy common numbers to use. Okay? So 0 and 100 seem to work a little bit better in that sense. Applications, though. In weather, for the US and medicine in the US, we use Fahrenheit always. Anything to do with like the body, near Fahrenheit. You're not going to use Celsius. For Celsius, you're going to see things outside of the US for scientific use. And then you're going to see a lot of Kelvin for specifically physics and physical science and astronomy. You're going to see things measured in kelvins. Especially things like the temperature of stars and different really, really hot celestial bodies. Things that are really cold will also be measured traditionally in kelvins as well. Okay, so low temperature physics, and then we're talking about things like gas laws. So let's look at this first example, very simple math. We have an example where we're told that the lowest outdoor temperature ever recorded on Earth was negative 128 Fahrenheit in Antarctica in 1983. In negative 128 Fahrenheit.
It's freezing.
It's way below freezing. Right, way below freezing.
It's like really cold, like freezing like that.
Yeah. Really cool. Let's figure out what that is in those other 3 scales. So let's start. I would not go to Kelvin first, because you don't have something to convert from Fahrenheit to Kelvin. But you can convert from Fahrenheit to Celsius or Fahrenheit to Rankine first.
Okay, well, Rankine is 31.
Why is it called Rankine?
I mean,
I think it's the scientist that came up with the scale. If you look up Rankine, I know Kelvin is. It's after the last name of a scientist. I think Rankine is as well.
sorry for being.
So I could start with this formula if I want to. Okay, that's one option to go with. Or I could start with this.
I did that one.
But either way, all I have to do is literally plug in a number. This is the easiest math you will really ever do in this class. Okay, plug in what you got, the negative 128.6, here and here. Come up with your Celsius and Rankine temperatures.
Celsius is negative 89. And your Rankine is 331.4.
Rankine is?
331.4.
How would I get the Kelvin scale?
Celsius plus 273.
Yeah, use the Celsius answer you got, plus 273.
183.7. Or 0.8. No.
Okay, so we're not even really close to absolute zero still. We're really still pretty far away. And that's the coldest temperature ever recorded on Earth. Whoa. Negative 128. All right. Take a look at the next slide so you can see what the homework